Hi everyone, welcome back to the GOCC. Today we have Dylan Snustad from Arizona State University speaking to us about labeled chip firing on star graphs. Before we get started, let's just remind ourselves of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that, Dylan, whenever you're ready, go ahead.
Awesome. Yeah, thanks for having me. Um, so yeah, I'm going to be talking about labeled chip firing on star graphs today. This is kind of work I've been working on with Annika Gonzalez-Zugasti and Ryan Lynch and myself. Um, I'm going to try and treat this as like a pretty informal presentation. So if anyone ever has any questions, feel free to like interrupt me or just like talk over me to get my attention. Um, yeah, the goal of this is kind of just to get people interested in chip firing and then kind of pivot into labeled chip firing. And then at the end, I'll kind of talk about some interesting results that we kind of looked at recently on these star graphs that I'll introduce later. But to start, right, I should start by kind of giving you like a vague overview of what chip firing is. Um, it's really just this kind of like discrete dynamical system and game. And kind of the headspace to be in is that you can think of this as like modeling resources in some sense. Um, So the idea is we're going to put a bunch of these like chips on a board that's going to kind of represent like money in some sense, and then we're going to distribute this money to different vertices representing like people in some way and see what happens at the end of the game. And chip firing is a pretty interesting area um, because it actually ends up being very interesting in like relation to other areas of mathematics and having lots of other connections in interesting ways. So there's like a generalization of parking functions called G parking functions that come up a lot. There's lots of connections to commutative algebra. You can think about interesting hyperplane arrangements that arise from this chip firing game. You can kind of recover like a discrete version of divisor theory, and you get like a discrete Riemann-Roch that kind of shows up on these discrete graphs in certain cases. That's kind of interesting to look at. It's also used in physics by some people, I guess. So there's some statistical physicists who kind of like this game, and I guess it can model phase transitions um, kind of neatly in these cases. And really, this game, the thing we're going to be interested about is this thing called stability, or this notion of stability. And this is going to represent our like end game. Um, so with that, I'll kind of start talking about the specifics of the game, right? So we're just going to start with any graph with a vertex set and edge set, right? And we're going to place Ci chips on vertex Vi. So here I placed three chips on vertex 1, maybe four chips on vertex 2, three chips on vertex 3, and then two chips on vertex 4. And this is going to represent like our initial state of our game, right? So we're starting from this configuration. And then kind of the turns of this game are going to be represented by time steps. And at each time step, we're going to choose a vertex that can do something called firing. Um, and when a vertex fires, it's just going to send one chip to each of its neighbors if we're playing on a graph, right? And so kind of the rule here is that in order to be able to fire, you need to have at least as many chips as your degree, right? So in this picture here, I have a vertex of degree 3. So if I want to be able to fire this vertex, I better have at least three chips on this vertex, right? Um, and so then the idea is we keep kind of just choosing vertices to fire and we keep proceeding in this way until eventually we get a configuration that's stable. And by stable, I mean no more vertices can fire, right? So every single vertex has less than its degree number of chips on it, right? Um, and then kind of a nice result that you end up getting from chip firing in this sense is this notion of global confluence. Um, and this is really just it's the idea that the way you play the game doesn't actually matter. So I phrase this whole thing as you're playing a game on a graph and you're kind of choosing which vertex to fire at each like time step. It turns out that it doesn't matter what you do. The end result of the game is uniquely determined by the initial configuration on the board. So then kind of a natural question is, right, if I start with some number of chips on my board, I want to eventually be able to stabilize, right? Where we're interested in this kind of end game. And so I always just throw this up as an example because this shows that in certain cases things don't go as you would want them to, right? So if I keep firing these vertices over and over and over again, you can do like a pigeonhole principle argument, right? And you can see that, okay, no matter how many times I fire, at least one of these vertices is going to have two chips, right? And if you have two chips, you can fire in this case because each of these vertices have degree two. So our game is never actually going to end. And so there's kind of two ways to remedy this as an issue. And I'm going to mention them both, but we're really only going to care about one in this talk. So the first is this natural modification where you literally just add like a trash can, right? So we say, okay, turn one of these vertices into a trash can. Now, every single time a chip gets fired into this trash can, it just leaves the game essentially. And so we call this kind of a sink vertex. Um, the sink is not allowed to fire, so the process has to terminate, right? Assuming your graph is like connected, you can see why this should hold true, right? So now if I throw any finite number of chips on my board in any order, even if it's a very, very large number, eventually the game will end, right? So I can recover this notion of like the end game, right? The final configuration, the stable configuration. Modification two, you can see this is precisely where I ran out of Bailey slides, so production quality is going down with my picture. But natural modification two is we can just add more vertices, right? And by add more vertices, I mean let's just plan an infinite graph, right? So if I don't want to introduce a sink, but I still want everything to stabilize, I can just keep adding vertices, right? And eventually these chips will just keep getting spread out further and further and further until eventually the game will end. And so the first kind of example of this that you might be interested in studying is this infinite path graph, right? Where you just have some infinite path just kind of running across your screen over and over, right? Um, the problem mathematically, is that it's kind of boring to study what happens here. And specifically, it's boring if we look at this case where I just want to throw a bunch of vertices on a specific vertex and then see what happens, right? So it turns out that if I throw a bunch of chips on vertex V naught here, and then I stabilize, if I start with an even number of chips, what's going to happen is I'm going to get M chips on the left side and M chips on the right side. And there's just going to be in a very specific spot, right? So there's going to be one chip at vertex V minus one chip at V minus two, one chip at V minus three, all the way down until there's like M of those vertices with one chip. And then we're going to get the symmetric thing on this other side. And then if I have an odd number of chips that I start with on vertex V naught, I'm just going to get an additional chip on this center vertex here, right? So this is like kind of boring. And even these two like proofs of this are just like easy induction proofs. So it's not like something super interesting. So what whoa, my desk just freaked out. All right. So what McConville Propp do in a 2016 paper is they say, okay, this global confluence thing is way too strong, right? It's kind of making the math not very interesting in some sense. So how can we make it more interesting, right? How can we try to like destroy global confluence? And so what they do is they label these chips now, right? So they say, okay, let's start with n chips on a chosen vertex V naught, label them, right, 1 through n. And now I'm going to impose this like additional rule, which is going to say that if I fire two chips, let's say I fire one and two here, I'm going to send the smaller chip to the left and the larger one to the right. So in this specific firing example, if I chose to fire one and two, one would go to V minus one and two would go to V1 here. And now the question is, okay, we've destroyed global confluence because now our chips have labels. Um, but maybe like something nice will still happen that we can prove, right? But that's kind of like the thought process going into this. And then if this was like a board talk, I would essentially just do an example like this. Maybe I'd choose like six chips. Because it's online, I'll just kind of go through what I'll claim will be me choosing random firings for this example, one through four. So let's just see, right? I'm going to start with four chips on vertex V naught, and I'm just going to fire this randomly. So maybe I'll start and I'll fire one and two, like I mentioned earlier, from V naught. So one will go to the left and two will go to the right. From here, I can only fire vertex V naught again, right? Because I need at least two chips to be able to fire. So I'll do that. Three will go to the left here. Four will go to the right. And I'll kind of continue this game again. So maybe I'll fire vertex V minus one. One will go all the way to V minus two. Three will go to the center. Now I can only fire vertex V1. I'll continue the game here until finally we're at our final configuration. And so something that's like kind of nice here is that you'll notice we're like totally ordered, right? So we just go one, two, three, four in perfect ordering. So kind of the natural question to ask is how likely is this to happen, right? And it turns out that for this four case, no matter what you chose to do, you'll always get this total ordering, this one, two, three, four thing happening. And so you might ask, okay, well, can you always do this, right? If I plug in any n, will it always be the case that my chips will be totally lined up in complete order? And the answer is like no, very quickly, right? So if you plug in the n equals 3 case, this provides like a counterexample to what I just said, where if I fire chips 2 and 3 here at the start, 2 will go to the left, 3 will go to the right. I'm stable, and I've lost my total ordering, right? I have 2, 1, 3 instead of 1, 2, 3. Um, but it turns out that if you always start with an even number of chips, no matter how you fire, the final configuration will always be sorted in this perfectly nice way. And the proof of this is like very difficult actually. Um, so I think the proof is like 6 to 8 pages of just introducing notation and then going through the proof. And then there's an additional like 3 or 4 pages just on like analysis behind everything going on here. Which is, I think this is always very surprising to people that this proof is so difficult. Because it seems like a very kind of natural statement to stay or to say maybe. And if we look at the odd case, so I just noted that the odd case doesn't have this nice property, right? But there's a very nice like open conjecture in chip firing that people are interested in, which essentially just says that if you take the limit, right, as n goes to infinity in this odd case, the probability of approaching this like perfectly ordered configuration will go to 1/3. And this is like very strong because it turns out that whenever you start with an odd number of chips on your board, the last fire will always take place with something that looks like this. You'll have 3 chips on one vertex essentially, and then you'll do that fire, and that'll be the end of the game. So really, what this conjecture is saying is, as n goes to infinity in the odd case, the probability of becoming sorted goes to 1 up to the last fire. And then you can see here that the 1/3 is coming from this like 3 choose 2, right? 3 different ways that you can choose to fire from this point, only one of which will be sorted.
Hey
Okay.
Dylan.
So yeah.
Oh, super quick. Can you control, like in the even case, can you control the gaps between the sorted chips? So like
Um,
in the m equals 2, so in the 4 case, you had like
mhm.
1, 2, and then a gap, and then 3, 4. Is
Oh, can you
this
control where that
something
gap is?
consistent? Can you like
Yeah.
make this distribution as wide as you want, or is this
This is stuck with this
like stable?
V0 gap. Yeah, so the stability will always just be everything will be clumped up with just the one V naught gap at the center.
Oh, okay. So it's always gonna be like 1 through m, and then v naught, the space, and
Yes,
then m plus 1 through 2m. Okay.
exactly.
Yeah,
That's exactly it. Yeah, yeah.
cool.
Oh yeah.
Uh,
So then,
could you remind me
oh,
of the condition on the label chip firing?
can you repeat that one more time? Sorry.
Could you remind me of the condition on the chip firing?
Oh,
The label chip.
yeah. So the rule is, um, if I choose any two ver like chips to fire, the smaller one always has to go to the left, and the larger one will have to go to the right. So
Mm-hmm.
here, when I fire, I have to choose two chips to get rid of because I have my two neighbors that I have to give chips to. And then whichever two or I choose, so maybe I could choose 4 and 2 as well. The smaller one will have to go to this side, and then the larger one will have to go to the right.
Okay, cool.
Um, oh yeah. So I mentioned that that proof is like pretty difficult for the 2M case or for the even case. Um, Klivans and Liscio recently, just a few years ago, um, came out with a much nicer proof of the same result, using something they call the chip firing order poset or the firing order poset. So what they do is they say, okay, we can turn this into a poset by saying our elements are going to be k sub j, where this is going to denote the jth to last fire at vertex k. So k is representing my labeled vertex, and then the sub j is representing the last fire, second to last fire, third to last fire that takes place on that vertex. And then we're going to give this thing an ordering by saying that k1j1 is going to be greater than or equal to k2j2 if k1j1 must occur before k2j2 in the firing. So kind of a weird poset to wrap your head around at first. But I have like a little picture here of what happens in two cases. So I have the poset for the n equals 10 case on the left, and then the n equals 11 case on the right. And so the way to kind of read this, um, I'll start with this 10 case. I think this is prettier to look at. Is that all the way on the bottom here, this little, can people see my mouse actually? If I move it? Okay, people can. Awesome. If I start with this kind of bottom point on my diamond here, this is representing the last fire that happens at vertex 0. So my center vertex where I started. So what this post set tells me is that for the even case, my last fire is always going to happen at vertex 0. So it's going to end where I started, essentially. And then this is going to represent my last fire at vertex -1, -2, -3, vertex 1, 2, 3, and so forth. And then as I go up, this is representing like the second to last fire at vertex 0, third to last fire at vertex 0, and all the way up. And so why this is so nice as a construction is that you'll notice I just mentioned you get this nice diamond shape kind of happening here in your poset. This is exactly what you need to be able to prove global confluence in the even case. So you can really leverage the structure of this poset to give a proof of why you get this nice total ordering when you're in the even case. And so Klivans and Liscio essentially turned what was a very like disgusting, difficult proof to follow with like not too much motivation into something very like easy to follow that's just a couple pages long now. And it's very useful because you can use the same idea and try to apply it to other problems in chip firing, which is what I'm going to talk about kind of on the next couple slides. It also is pretty neat because it gives intuition behind why the odd case is so difficult to prove. Specifically, this like odd conjecture I mentioned. It's because this poset structure breaks down and disintegrates very quickly. So here with the n equals 11 case, you can see you kind of get this diamond structure, but it's like malformed in some sense where you can't really work with it anymore. And so that's kind of like the reasoning behind why this is such a hard problem to solve when it's odd. So using this kind of poset idea has been kind of interesting. So there's been recent works, I think in 2023, Musiker and Nguyen kind of extended this idea of chip firing on the path graph, the infinite path graph, to working on binary trees. Um, so they essentially created a new rule where they said, okay, now when a vertex fires, let's say I'm starting at the top and I'm gonna fire my vertex here, the smallest vertex will go to the left. The middle will take this little loop path, which is needed for some non-obvious reason at first. And then the largest chip will go to the right. And then if I do a fire down here, further down my binary tree, I'm going to continue with the same logic, but now the middle vertex will go back up to the parent. Um, And this is kind of an interesting idea that people have been looking at, and you can use this poset structure. It turns out that you can exploit the same like end game, they call this the end game diamond, to prove similar sorting properties in these cases. But you don't get the full confluence, like the full sorting like you did before. And so this is actually kind of nice because it opens up different avenues for like classifying the types of configurations that can happen, the final configurations that can happen up to this sorting rule. And for these binary tree cases, that rule tends to be something like if I look at any vertex here and I go all the way to the left and all the way to the right, this subtree, which in this case is the whole tree, will have the smallest chip all the way to the left and the largest chip all the way to the right. Right. And then if I take this subtree like 1, 2, 3, you can look at and get a similar rule where you get 1 in this case is all the way to the left, 3 is my largest chip in this subtree, and 2 is like my middle. So this is something that people have been interested about really recently, actually. Um, Ryota Iganaki, who's friends with me and Bailey, has recently been interested in applying this to like a k-ary case as well. So what he did is he took this binary tree case, added the k-ary tree to it, and then proved the similar results, and is now trying to classify all the possible final configurations that can happen. So at least it's some like nice, interesting math. So with that, I can kind of get to, what we were interested in. And really it stemmed from these kind of papers where the idea was we can really only play this labeled chip firing game on two types of graphs so far, or at least that I know of, which is this infinite path graph and this like binary tree case or k-ary tree case. So it'd be nice if you could like kind of generalize what's going on here in some nice way. And what we came up with was this k-star graph idea. Um, Specifically like an infinitely subdivided k-star graph. So here I have a picture of this 7 star. And what I mean by that is I'm just going to extend each of these legs out to an infinite path graph in each direction. So each of these little legs is actually an infinite path graph kind of going through, or that starts at this center vertex and keeps going. And so when we do label chip firing, I need to give you a rule, right? Some sort of like local sorting property that we're going to hope extends to some sort of nice global sorting property, right? And the idea here is let's label the legs 1 through k. So maybe I'll start here. I'll call this branch 1, 2, 3, 4, 5, 6, 7. And now if I fire at the center vertex, I'll send the largest chip to branch k, and I'll send the smallest chip to branch 1. And then I'll send the second smallest chip to branch 2, and I'll kind of continue along with this idea. And when a non-center vertex fires, what I'm going to do is I'm going to fire the smaller chip back towards the center, and the larger chip will go further out, essentially. So we're kind of generalizing this. You can think about this as being a generalization of the two case, right? So if I look at the 2-star graph, this is very similarly related to the Klivans Liscio or the McConville Propp um, game up here. But there's a slight modification that I want to point out, which is that even in our case, if we're looking at a 2-star graph, when I fire something off of the center vertex, the big chip always is going to go out. So our game rule changes slightly. So for instance, if I fire 3, 1 here, normally 1 would have gone to the left and 3 would have gone to the right. Now I'm saying that big is always going to go out. So in this case, 3 will go into -2 and 1 will go to V0. So one of these branches almost says like they're ordering swapped in this specific case. Um, and then the question is like what happens, right? So from this standpoint, can we enforce any nice like sorting properties and work with that? So it turns out the answer, if n mod k is not 0, the answer is no. There's nothing nice you can say for the same reason as why you can't say anything interesting in the odd case necessarily for the classical chip firing on the path graph. Um, but you can let n be km. So if k is my number of chip or my number of branches, I'm basically just going to look at multiples of k, right? And when we do this, then the final number of or the final configuration of chips on the board will behave very nicely, where we'll get 0 chips on this center vertex here. And then if n is km, I'll just get 1 chip for the next m vertices outwards. So if I plug in n is equal to 9 for this 3 branch case, I'll get 0 chips here, 1 chip here, 1 chip here, 1 chip here. All of these next 3 will just have 1 chip on them. So the final configuration is easy to classify at least. And then the main result is pretty nice as well. So it turns out that, again, this is kind of just, this theorem is kind of wordy, but all it's saying is if I look at any specific branch, so here I have branch B1, and I start from the bottom and work my way up, I'm always going to be increasing. So here I go 1, 4, 7, 2, 3, 8, 5, 6, 9, right? So it turns out using this like Klivans poset idea, I'm able to somehow show that we always get some sort of nice sorting property along each branch. And kind of the main tool that we did, that we used to prove this was this chip firing poset by Klivans and Liscio. So we call this thing kind of the book poset in the context of this star graph. Because what ends up happening is, maybe I'll go back up to it. You see we get this nice diamond in the initial case on the path graph. Really, you can think of what's going on here is they're looking at the 2 branch case. And each half of this diamond is representing one of those 2 branches. And so when we continually add more and more branches to our graph, we're adding more of these like half diamonds into our poset. So what's happening is we're just gluing a bunch of these half diamonds over and over and over again into our poset, and you get kind of this like book structure. Maybe you can kind of look at it like that, where each branch is kind of representing like a page in this thing. And then from here, this gives us everything we need to be able to prove this nice theorem, which says that we have to be increasing as we go out. Are there any questions about this before I move on? So then from here, the next kind of question to ask is what are the types of final configurations that can occur? Right? So we only know one thing by this theorem, right? Which is that really you just have to be increasing along each branch. This still leaves open a lot of final configurations that could occur, right? Um, so you always start with a toy case, and this is kind of the one I wanted to talk about because I think this is maybe like the cutest example, right? Um, so let there be like k branches, and we'll just look at what happens when there's 2 k chips starting on the center vertex, right? So what we can do is we can kind of organize this as a Young diagram, which might give away the punchline maybe. Where we're going to say, okay, that final configuration, we're going to represent each of these branches as a column of this Young diagram. So here I have this shape KK, right? Each one of these columns is representing some branch. And when I fill this with a chip, it's going to represent the chip at the vertex here, and then I'll have a chip at the vertex here as well, right? So that's like how this filling is going to go. And now what I'm going to do is I'm going to say, okay, I only have 2 k chips on the board, right? So the first fire is going to let me fire k-chips, which here I'm just representing this as like A, B, C, D, E, F, right? Just to get a vibe for what's happening. And I know that A is going to be less than B, is going to be less than C, right? Is going to be less than D, E, F. So I know that this is row sorted, essentially, because my chip firing game tells me it has to be. And so this kind of lets us fill in that first row in our diagram. And then what happens is we still have another k chips left in the center of our graph. So we have to do that fire next, essentially. And this gives us the same relation here. So we have G is less than H is less than I is less than J is less than K is less than L. And now there's this very nice kind of like fact that you can use, which is that if a matrix is row sorted and we column sort it, the resulting matrix is both row and column sorted. So this is kind of like a fun like induction bubble sort proof type vibe that you can do. But the idea here is I have this kind of um, filling here where I've kind of stuck two objects in each of these fillings. Both of them are row sorted. So when I column sort them, all I'm doing is I'm doing a row and column sort at the same time. So the initial firing from the center vertex gave me my row sorting. And now the chip firing rule on the branches is going to give me a column sort in some sense. So from this nice kind of fact, I know that A is going to be less than H is going to be less than I, less than D is less than K is less than F, no matter how I fired this. And then whatever gets back to the center, so I kind of push these guys back out because this is representing them back on the center vertex. When I fire this again, their order is not going to change at all because all I did was just column sort. So both rows in this sense, where this is one row and this is one row, are still row sorted. So when I fire back, we're left with SYT. So it turns out that whenever you're in this case, you're actually discounting the Catalan numbers. So we've recovered the Catalan numbers by chip firing. And then the next question you might ask is, okay, well, do you get all of them though? Right? Do you get all of the Catalan configurations? Oh, and maybe I should mention, if this is a fact people are not aware of, a standard Young tableau of this shape, their fillings are in bijection with the Catalan numbers. So they count the Catalan numbers. So this is like kind of cute, right? And it turns out that you can always get any SYT as well, because all we're going to do is, if this is some arbitrary SYT, this filling here, I'll just fire the first row. I'll choose to fire all of those chips at the same time. Then I'll choose to fire all of these chips at the same time. And I'll just kind of keep firing them in rows like this throughout my chip firing game. And so what happens is I'll always be kept in my SYT configuration. So you get this nice kind of injection property where, maybe do I say this on the next slide? Yeah. Where given any SYT of shape, I use matrix notation here because I'm using this kind of block shape. So given any like K by M shape, you can always get any SYT that you're interested in by firing sufficiently like smart or clever. Um, so this makes you like very hopeful for things going well. However, more complicated configurations can occur. So here I've put a picture of one of these for the 3-3 case. So K is 3 and M is 3. And here, if this was going to be represented as an SYT, so I have, depending on how you want to look at it, I have my rows increasing or my columns increasing, right? 1, 4, 7, 2, 3, 8, 5, 6, 9 is fine. 1, 2, 5 is fine. So now I'm going this way to get my other increasing that I need. But this 4 and 3 kind of ruin my day. So I get this 4 decreasing to a 3. So it's possible to get final configurations that are not, nice standard Young tableau in this sense. But then kind of the natural question from here is to ask like, okay, well, what can you get, right? So there's like a sufficiently nice type of final configuration. Can we kind of extend this thinking to figure out what goes on in different cases? Um, and the answer turns out to be very difficult. So in general, classifying these, right, both from a computational perspective and a theoretical perspective is not obvious. So computationally, if you were trying to check every single possible firing output that you could do, this like explodes. So like this is not a valid strategy. So this is a table kind of showing for different M and K, right, the number of possible final configurations you can have. And you'll notice it's not very big, right? Because it just explodes. I think even doing like this 3-4 case or this 4-3 case took the computer running like over a couple days, essentially. Um, and then theoretically, trying to classify these twists is very difficult. So in the two branch case, you can construct a nice bijection with lattice paths. So you can say, okay, for every one up I go, I can only go Gauss's counting number of steps to the right. And this ends up being a nice classification for what happens in this two branch case. So this table here, or this kind of line here and this line here, are well understood. But even building up to the three case is very difficult. So if M is 3 or K is 3 and you want to generalize the formula, this is not obvious. Um, and we think we know what's going on for the K equals 3 case, um, where we can kind of generalize this like lattice path idea that I just mentioned earlier. But the construction is very kind of gross, right? And so I didn't really want to talk about it too much in this presentation because it gets overly complicated and it's not very pretty to look at. Um, and then I just kind of put like the corresponding table here. So this is going to represent the number of non-SYT configurations, and you can kind of show how this grows as we're going up and up and up, right? So initially we start off with like zero non-standard Young tableau configurations, essentially. And then this is going to continue to grow as we kind of expand out the table here, which you would expect, given how fast like the number of these things expand, right? So like the number of fillings for a table grows so incredibly fast, right? Um, but there is kind of like an interesting question to be asked here, which is, does the probability of you reaching one of these nice configurations, nice final configurations, like reach zero, or does our sorting property somehow like hold its own enough to where somehow the probability of reaching one of these SYT configurations doesn't completely go to zero as Km goes to infinity in some sense. So this is like kind of an analog to that like one-third conjecture that I mentioned earlier, where these like probabilistic questions are somewhat interesting to answer. And in this case, there's a lot more hope for being able to figure out what's going on here because I'm still in my poset structure. So I haven't left my nice poset here. So being able to bound what's going on should definitely be possible. Whereas in this, like the one-third conjecture, things get a little bit more difficult because you break your nice diamond at the end of the game, right? Um, so things get a little trickier. Okay. So with that, there's kind of like a nice open problem that we're currently kind of working on, which is that in chip firing, there's this general phenomena of if I'm given a final configuration, I can check if this configuration comes from a nice place. So like there's this thing called like Dar's burning algorithm, and there's like other nice burning algorithms or more general algorithms in chip firing that essentially says if I give you a configuration, can I quickly check if this thing is valid somehow, right? So can I actually get here? So kind of the question rephrased here is that for arbitrary Km, is there some quick way to check if a proposed final configuration is valid, right? Can I use some sort of like valid number of checks to quickly determine if this is something I can actually worry about or not? Um, and then I mentioned this at the end, but literally just if you can fill out any more lines in this table for k is greater than or equal to 3 or m is greater than or equal to 3, this is also something that we're kind of trying to think about and work on. So yeah, with that, I think I'm done. So thank you guys for listening in.
Thank you so much, Dylan, for such a wonderful talk. Are there any
Yeah, thanks for
questions?
having me.
I have a question. So you touched on like some of the relationships between this and like how there's like connections to algebraic geometry. Um, uh, just is like this labeling of the chips, is that something that has like an analog in algebraic geometry that you know of?
this specific context, I don't think has an analog that I'm aware of. So the way this normally goes is, if I'm remembering this correctly, which I could not be, but so in chip firing, you're able to recover this like equivalence class that gives you like a group structure when you don't label the chips. And then I think the way this goes is that you can mod out what's happening for each of your final configurations via these equivalence classes. And then that kind of leads you into this notion where this critical group that you're interested in becomes an analog of like your Picard group, if I'm remembering the word correctly. Maybe an algebraic geometry will let me know if I am. Um, so you get
I
these
think
like,
Picard group is the set of equivalence classes, I think. Yeah.
yes, okay,
Um,
great. Yeah, so you get this like analog here. But in this labeled case, things
oh, there.
break down.
Oh, there. Yeah. Yeah, cool.
Yeah.
Other questions for Dylan?
Yeah, I really liked your exposition, was very clear. Uh,
No, thank you.
Question about, so you showed the three case, right, where it was the non-SYD configuration.
Mm-hmm.
And by your theorem, I think we know that they're always increasing.
Yes, along the branches. Yeah.
So, and so that means the rows are always increasing, but not necessarily the columns. Is that
Yeah,
what you're?
exactly.
And there is no way to maybe start with a configuration where all the branches are increasing and then reconstruct how it was reached?
Um, Not that I'm aware of.
Okay.
So
Uh,
you're saying like
for
if I
example, could
start
you?
with, are you saying like if I
Yeah,
start with this configuration, can I reconstruct the firing path to get there? Or
yeah.
like, yeah, this is a difficult problem.
Okay, I see. Uh, so if it doesn't like biject onto standard young Tableau, could it biject onto some other sort of Tableau? Because you do have increasing rows. Uh,
Yeah, this is something that would be very interesting to look into. I think we try to spend like a little bit of time looking at different types of fillings that just have this
Mhm.
like row sorting or column sorting property, however you want to look at it. We couldn't find
Mhm.
anything, but it's very possible that there is some like well-known type of filling, right, that satisfies this game or that's in bijection with the final states of this game.
Yeah. Uh, we can talk about the this after.
Sure.
I think
But
we'll
yeah,
get into.
this table we have, at least like if you just type it into OEIS,
Hmm.
doesn't give any immediate results. But obviously that's not a very thorough search. But yeah.
Yeah, it's also like less number of terms.
Yes,
Mm.
it's also very, things get very low, right? There's not too much to work with.
Any other questions? I might have a quick question, Dylan.
Yeah,
So
sure.
if you go back to like the infinite path at the very beginning,
Hmm.
so in the even case, you said that like regardless of your firing pattern, you always get the fully sorted permutation of chips at the end.
Yes.
In the odd case, can you characterize like all the possible permutations of chips? So like one or at least describe their features. So like one will always have to lie on the left or in the middle, and then like n will always have to lie on the right or in the middle. I'm just curious, can you like count how many permutations are achievable by some firing pattern of an odd
Yeah,
number of
even
chips?
this is very difficult. Um, so I think what happens, so for the five case, like if I just look at this,
Hmm.
you can always force any chip you want to end up in the middle somehow. So like what you can do is I can add the fifth chip here, and then I can pretend the fifth chip is just not there. And I can do
Yeah,
my
and just
normal
not fire
for.
it ever. Yeah. Yeah,
exactly.
yeah.
So
Okay,
because of
cool.
that, it makes like characterizing these very difficult. But I'm sure someone has tried to do
Mhm.
it. But yeah.
Gotcha. Yeah, like in the three case, you have the three possible sortings, right? So that's somehow like half of the total permutations. Um, so I don't know. I was just wondering if it's like some well understood number, like it's always half of them, but maybe not.
Yeah, not that I'm aware of.
Okay. Cool. All right. Well, let's
Quick
thank Dylan again.
question.
Oh,
Actually, before
yes,
we
go
do that,
ahead.
I have a quick question.
Yeah.
Um, so have you or anyone you know of these similar concepts, but in a probabilistic form? Like, let's say, for example, you have chips, but they fire with likelihood P, and you assume some distribution of doing so. I only asked that because I have thought of chip firing on a separate project of mine in that context, although we haven't quite looked at these particular patterns that you're observing. But I've always wondered if other people besides me have thought of chip firing in their own ways using probabilistic means and then trying to study the distributions you get of all the different configurations and whatnot.
Yeah, this isn't something I've ever looked into, but I do know it's like this is like a interesting problem to look at, right? Because like you get the stochastic process given by your critical group, right? You can kind of define it in this like Markov chain sense. And I'm sure there's something similar that you could construct for like this labeled chip firing thing as well. But yeah, I don't know anyone who has looked at it in this probabilistic setting. I feel like there's just a lot of these like probabilistic conjectures, and I don't think anyone has been able to make any like real progress on them. So no one has like done like the full analysis that maybe would be interesting. Yeah.
The context in which I look at this is more through the lens of epidemiology. So, like, if you have like some graph structure that represents a population, and chip firing would model like some disease propagating through the population in some sense. We've been looking more at just getting like summary statistics of like reproductive number and like how things like the average infection time could affect like the distribution of how the chips would spread throughout the network to see like in a simulation sense, does your disease die out? Does it go endemic or does it kill everyone? But we hadn't really done much work trying to like rigorously prove like, oh, in any generic Markov chain chip firing process, you always get these stabilizing results. It's something I would like to do, but I haven't had the time to do it. So I was curious to see if anyone had beat me to the punch on it or thought about it in a different way.
Yeah, no, not that I know of. But yeah, that'd be a very interesting
Okay.
question to look into. Nice.
Okay. I,
Awesome. Thank you again, Dylan.
Yeah, for sure. Thanks for having me.